Okay, yeah, recording started. All right, yeah, so I was going to start with a quick review of the rigid body velocities. Oh, they can't hear me. I don't know. Is that better? I'll talk really loudly. What's up? Oh, could it be the internet? Yeah, let me try something real quick. Actually, I'll grab my earbuds and then I'll see if that improves the mic. Okay, I don't actually have my earbuds. I'm sorry. Okay. Like, is it really bad, the audio, or how does it sound? I'll talk a little bit louder when we actually get started. Are you still there? Oh. Okay. Okay, I think it sounded okay on the previous recordings when I checked those out. Okay, let me know if the audio drops out or anything, and then yeah, we can try something else. Okay, thank you. Okay, yeah, so we were just going to start with like doing a quick review of rigid body velocities, just because those are an important part of Jacobians. They come out a lot. Oh, sure. Okay, cool. Yeah, so we were going to start out by doing a quick review of rigid body velocities, and then following that, we were going to start to talk about the manipulator Jacobian. So manipulator Jacobian, right? So like what it is, where it comes from, and why we really care about it in robotics, why it's important. And then following that, we were going to talk about singularities of the Jacobian. Okay. So just for this last part on singularities, what I wanted to aim for was more of a like a conceptual overview of where they're coming from, because I think it's more or less mostly straightforward to check like linear dependence of columns, especially if we give you a particular configuration. So I think it's really important to just have a good geometric understanding of where those are popping up. All right, cool. So do we have just any questions, administrative or otherwise, before we get started, or how are we doing? Good, nice. All right, cool. So we can talk about rigid body velocity. Rigid body velocities, real quick. Okay, so just as an overview for what I'm going to say about these here, since we actually covered them, in full detail last week, here I'm just going to talk about like a general conceptual overview, some like highlights or key points of what rigid body velocities are and what we're really going to need for them when we're talking about Jacobians today. Okay, cool. So what are they? Okay. So remember that rigid body velocities are those big like 6x1 vectors, right? And they're not physical velocities, but they're transformations that help us find these physical velocities. Okay. So they are transformations that help us find physical velocities. Okay. And it's not just the physical velocity of one point in particular, but it's something that will hold for every single point on our rigid body, right? So if I have like a rigid body like my pen and I'm spinning it around, these transformations will help us find out how quickly every single point on there is moving just by plugging this point into the transformation. Okay, so it's a really, really nice thing that helps us do a lot with describing the kinematics of rigid bodies and robots. Okay, so what do they look like? So if we have a transformation G, we have a rigid transformation G. Remember, this is one of those like RP01 matrices in SE3. We can find the velocity that's associated with that transformation by doing the following, right? So V hat spatial, we say, is equal to the derivative of G. We denote that with this little dot right here. So that's the derivative times the inverse of G. Okay. So this gives us something called the spatial rigid body velocity. So spatial rigid body velocity. Okay. So what does this actually look like when we write it out like term by term? Right? What are those terms going to look like? Well, if we write out this matrix V hat S, right up here, we're going to have this omega hat. We're going to have a V and a 0 and a 0. Okay. So this is one of those like 3x3 skew symmetric matrices we say. This is a 3x1 vector. So overall, this is going to be a 4x4 matrix, right? Element R 4x4. Okay. So why do we call this the spatial rigid body velocity? What's it actually doing for us? And why do we care about this form? All right, well, let's check that out. So how do we use it? How do we use it? Well, let's imagine that we have some point, right? I'm going to call it a point QA in space, right? And when we spin our rigid body, and when we spin or move our rigid body, we want to figure out what's happening to this point QA, right? If I have my pen here and I'm spinning it in space, maybe I'll pick QA to be on the tip, right? So when I'm moving it around, I want to figure out what's happening to that point. So when we spin or move our rigid body, how fast is QA doing? QA, right? We can answer this question using our rigid body velocity transform, right? So what it tells us is that in homogeneous coordinates, right? I'm going to use this QA bar to denote homogeneous coordinates. The time derivative of that point, right, which is equal to the physical velocity vector, right? Like actually how fast is moving the x direction, the y direction, the z direction, is equal to the following. It's equal to this v hat spatial times our point in homogeneous coordinates. Okay. So whenever you see one of these v's or these v hats, just remember it's an actual map from our point in homogeneous coordinates into its velocity in homogeneous coordinates. Okay. So this is our point in homogeneous coordinates in the spatial frame. Okay. And this spatial rigid body velocity is taking us from our point in our spatial frame to its velocity vector in the spatial frame. So velocity vector in the spatial frame. Okay. So what's really important to remember is that these VS's and VB's, which we'll talk about in a moment, they're not the actual physical velocity. They're just transformations that help us find the actual velocity. Okay. So V hat S is a transformation which helps us find physical velocity. Okay. So just like we have this little hat map on here, right? In the past, we were always talking about these hat map vectors, like omega hats and xi hats and all these different things. We know that we can take this hat map vector, turn it back into like an actual vector, right? So at the moment, it's in a hat map, right? It's going to be a matrix, R 4x4, right? That matrix that we talked about right up here. So if you want to go back from this matrix and pull out all the essential information, put it into vector form, we say that we take the V map, right? So V map takes us from our matrix back into the associated vector. Okay. So if V hat S has the following form, okay, it has some omega hat S, some little VS, a 0 and a 0, and we try to take its V map, right? V hat S. We just write this little V up here to denote that we're doing the opposite operation of a hat, right? And all that's going to do is it's going to extract all of the necessary vector information from that matrix for us. Okay. So up top, we're going to write V hat spatial, right? We're just going to take that guy out. And then we're going to take this one, right? Omega S. All right, perfect. Okay. And when we write this in this form, right, when we take the V map of something, another way of writing this is just by dropping that notation. Okay. So whenever you see one of these V's without this little hat above, this is going to be instead a 6x1 vector. Okay. So it's going to be an R6. All right. So we now just represent the idea of this transformation in a vector. Okay. So whenever you see one of these 6x1 vectors that's referring to a rigid body velocity, just remember it's not the actual physical velocity vector of your rigid body, right? It's just something that when we take its hat map, it gives us a transformation that helps us find the rigid body. Okay. So when we take hat map, when we take VS hat, we get our transform. Okay. So once again, for those of you that just came in, we're just doing like a general overview of the stuff we'll need from rigid body velocities to talk about Jacobians in a more comfortable manner. So do you guys have any questions about this spatial velocity stuff that we've been talking about? How are you feeling? Good. Cool. All right. So this was our spatial velocity, right? And we know that it returns velocities in the spatial frame. Spatial frame. Okay. But a lot of the times we're not just going to have this spatial frame, right? We're going to have a lot of other different frames on our rigid body. Maybe we'll have a frame that's actually attached to the rigid body itself, right? So if we have a frame attached to the rigid body, what do we call that? That's just called the body frame, right? That's our body frame. We denote that with the letter B, okay? So if we want to try and find the velocity in our body frame, what are we going to do? So our body velocity is defined as the following. So v hat b equals g inverse times g dot, right? Where g is the transformation between spatial and body. And okay. So this is what we call our body velocity. Okay, so what's this thing actually doing? Well, earlier, remember, we had said that this spatial velocity, right, this v hat spatial, will take us from a point in the spatial frame, and it'll give us back its velocity in the spatial frame, okay? So this body velocity is going to do something really, really similar to that, all right? So what the body velocity does is it takes in a point in the body frame, and what does it return? It returns the spatial velocity of that point, as seen from the basis vectors of the body frame, okay? So as seen from the basis vectors of the body frame, okay? So what I'm going to say is that if I have some point QB in my body frame, right? So point, body frame point, and I apply v hat b to it, what am I going to get back? Well, I apply v hat b to that point QB in homogeneous coordinates, all right? And what's returned is the spatial velocity of that point, right? But just seen from the body frame, okay? So this is the spatial velocity of QB seen from the body frame, okay? And just like we were able to take the V map of our spatial velocity vector, right, our spatial rigid body velocity, we can do the same thing for the body velocity, okay? So if we want to take the V map of V hat B, right, we're just going to call that VB, all right? And once again, that's just going to be the same like 6x1 vector, okay? All right, so do we have any questions about this one real quick? Oh, yeah. So once again, we're just going through this a little bit quickly. If there's anything here that you'd like to see like done out in full, just let me know, and then we can go ahead and cover that. But yeah, is that good? Yes. Okay, perfect. All right, cool. So one question that we had got into all the way at the end of last time was what the relationship is between these vectors, right? Like, how do we relate? How do we relate VB and the spatial, right? What's the relationship between those vectors? What's the relationship between their hat maps? How do we describe that sort of thing? Okay. So what we want to do is we want to transform a rigid body velocity VB from the body frame into the spatial frame. Okay, so how do we do that? So one way we can do this is, once again, I just won't work this out here, but one way we can look at this is by looking at those definitions that we started with, right? V hat S is equal to G dot G inverse, and V hat body is equal to G inverse G dot, right? Where G was this transformation between the spatial and the body frames. Okay. So how do we actually relate these two using this definition? Well, something that we could find if we do just a little bit of manipulation is we'll get back V hat spatial is equal to that transformation G times V hat body times G inverse. Okay. So using just this matrix G, right? We don't have to use G dot at all. We were able to figure out a transformation between our body frame velocity and our spatial frame velocity. Okay. So just using G, we go from V hat body back into V hat spatial. Okay. This was a kind of handy transformation, right? Because we only really needed a single matrix to do this, right? We only needed one of these G matrices of the form RP 0, 1, right? That was pretty good, but we didn't only want to have this transformation between these hat maps, right? What we wanted was something that that takes us from like one vector to another vector, right? So how do we write this transformation? Right, this transformation in terms of the vectors, right? So this time, instead of looking at these hat maps, we're looking at the actual underlying vectors, VS and VB, right? So VS and VB. What's the relationship going to be there? Okay. And we found last time that based on this relationship up here, we were able to define this really special matrix called the adjoint that helped us out and did this exact thing for us. Okay. So what this told us was that VS is equal to something called the adjoint of our transformation G times VB. Okay. So let's just break down this relationship real quick. Just make sure that we're all on the same page regarding what's going on here. Okay. So the adjoint of G is a matrix that transforms velocities from our body frame D into the spatial frame. Okay, so remember in this case, VB is a 6x1 vector and VS is a 6x1 vector. Okay, so the adjoint is a map from the space of 6x1 vectors, right? From the space of all body velocities out there into the space of all spatial velocities, which is also in our sense, right? So because of this, the adjoint of G was a 6x6 matrix, right? It was this huge matrix that was operating on these vectors. And the actual form of that matrix was the following. It was the rotation matrix from transform G. It was the hat map of the translation, right? Multiplied by a rotation matrix with a 0, and then another rotation matrix down there. All right. So this transformation, expressed by this big 6x6 matrix, was something that helped us transform our velocities from one frame to another. Okay. And it's called the adjoint of G because all these different entries in this matrix, they only depend on the entries of our matrix G, right? So entries only depend on G, right? Where G was that matrix RP0. Okay. So let me just write a quick summary of what we have up here. So in general, what we said was that we were able to define two velocities, right? We had our spatial velocity and our body velocity, right? And this was a transformation that takes us from our points in the spatial frame to velocity in the spatial frame. Okay. Now, similarly, what we said was VB was it contains all this information about this transformation that takes us from points in the body frame, to the spatial velocity of those points as seen from the body frame. Okay. Spatial though of those points as seen from okay, cool. Now, finally, our last conclusion right here was that we were able to figure out a transformation between these two in two different forms, right? One of them was in the hat map form. So we said v hat s was equal to the transformation between those two frames. Oh, yeah.
Transformation that takes us from our point in S frame.
Yeah. Oh, sorry. Yes.
Okay.
Yeah, that's right. So yeah, so we had said that v hat s was equal to the transformation between frames s and b, right? Multiplied by our body velocity times the inverse of that transformation. Okay. So this was one form of writing that transformation. And then we also had that second form that did the same exact transformation, just acting on the individual vectors this time. Okay. So we said vs, not the hat map this time, our actual 6x1 vector, 6x1 vector, vs was equal to the special matrix called the adjoint of G multiplied by v body. Okay. Right. So these are two kind of important relationships right here that we'll see popping up a lot today. Okay. So that's more or less all we had to do to review our rigid body velocities here. This is going to be pretty much everything we'll need for our study of Jacobians, where they come from, and why we like them. So do we have any points or like lingering questions about rigid body velocities that we want to go over before we move on to Jacobians? How are you guys feeling about this? Yeah. Yeah. Yeah, that's right. So Vs was equal to that little component of linear velocity, and then our omega spatial length. Yeah. And then, yeah, similarly, Vb was little v body frame, and this omega in the body frame. Okay. Yeah. Yeah, sure. That's good. Okay, sure. Yeah, is there anything that anyone missed writing down? I can scroll back up. Okay, I think Colin's just copying down. Yeah, further up. Okay, tell me when.
Yeah.
Okay, cool.
Minus second entry of that.
Yeah,
That's due to regulation.
that's right. Yeah. Sure, yeah. Yeah, sure. So we were just talking about the rigid body velocity stuff from last time. We were just doing a quick review. Okay, cool. So with that, oh yeah, just one more time. Are there any other questions? Yeah. Oh yeah. So p hat times r. What is that? So earlier, in the class, we were always talking about like these hat maps of like 3x1 vectors, right? So we had like omega hat, right? And if we did omega hat times some other vector v, that was the same thing as taking omega cross v. Okay. So what we're saying in this term is that we have an r, a p hat r, a 0, and an r. So p hat in this case is one of these like cross products, or skew symmetric matrices, right? So if we actually go ahead and we multiply this out on a certain twist, right? So let's say we do r0, p hat r, and another r, and we multiply that by some velocity in the body frame and some omega in the body frame, right? So this is equal to our VB right here. So what we see is that this is something that helps us adjust here and figure out what our body, excuse me. So this is something that helps us figure out what our spatial angular velocity will be in terms of the components of this one. So if we actually go ahead and perform this multiplication, we get an r times VB plus p hat r times omega b, 0, and an r. Okay, so what this thing is really doing up here is it's saying, okay, we know that this guy is going to be a component of linear velocity up here, linear velocity, and we know that we've actually translated some amount p between these two frames. Okay, so we know that whenever we translate and we have a rotational motion, we can capture the amount of velocity that's happened from that by doing like omega cross r, right? So if we translated some amount r, we're going to have omega cross r contributing to our linear velocity. Okay. So what this p hat times omega is doing is it's really giving us that effect in the transformation of saying, okay, this is going to contribute this amount to our actual spatial velocity now that we've shifted in this way. Does that make sense? Okay. Okay, cool. All right. So we can talk about the manipulator, Jacobian. All right. So this is our main topic for today. So we're going to talk about the Jacobian. We're going to give somewhat of an informal derivation of it that I think might be a little bit easier than what you guys saw in lecture. Then after that, we're going to give an example of how we might find it for a simple robot, and then talk about when singularities of this Jacobian arise, how we deal with those. Okay. So our main question at this point, right, is so far we've been just developing like all this different theory about kinematics of robots, right? We have forward kinematics, inverse kinematics. We now have all this great information about rigid body velocities, right? How quickly these things are actually moving in space. But we still yet to apply it to our actual robot theory that we were developing earlier. Okay. So our main question is, how can we apply the theory of rigid body velocities? Rigid body velocities. Define velocities associated with robot arms. Okay, so if I move my arm around, right, pretend that that's a robot manipulator, how would I be able to apply this idea of rigid body velocities to figure out, what the rigid body velocity at the tip of my hand would be, for example, right? Because once we have this rigid body velocity, we have something that allows us to figure out the velocity of every single point on our robot arm. Okay, so once we have the spatial and the body, we can get the velocity of every point on our robot. Okay, this is something that's really valuable, right? So say, for example, we're trying to develop a controller for our robot, right? And we want the tip of our robot to have some certain position and velocity in space. If we actually want to formulate that, right, and have an idea of what joint velocities that's going to require, this is going to be something that's really important for us to know, right? So you guys will probably talk about like a PD controller sometime next week. And this is something that involves knowing both the position and the velocity of your robot in space. Okay. So we have the position down, right? We did forward kinematics earlier. Now we need to figure out how we're actually going to tackle that velocity component, right? Once we have that, it's really going to open up a whole world of different things that we're able to do with these robots. Okay. So do we have any questions just about like the motivation or like why this is something that we need to care about? So, what's up? Oh, yeah. Sorry, that's a yeah. All right. Okay. So here's our basic idea. So here's an idea. Something that we know how to describe at the moment is how quickly we're just revolving around a single axis in space, right? So say I have this axis, that's my pen right over here. If I'm just spinning around that, right? I know that I could give a speed in radians per second, right? The amount that actual angle is changing. And that's a super precise way of giving velocity, right? So we know we can describe a rate of spinning. Rate of spinning with these theta dots, right? So if I take like my angular position, right, I take its time derivative, that's going to give me how quickly I'm spinning around a certain axis, right? But this is only rotational, right? So our main problem, this is only rotational. Only rotational. Okay, so how can I convert these theta dots into an actual physical velocity vector? Well, we've been doing some of this in the past, right? This is how we sort of derived a lot of our ideas in rigid body dynamics and rotation matrices and all this great stuff. But our problem isn't only just with one theta dot, right? Now we have these systems of arbitrarily complex robot arms, which is going to make things really hard for us, right? Because this system is all entirely coupled now. Right? We have all these different vectors and all these different theta dots that we have to deal with. Okay. So what we want is the following. We want to find some map that takes us from a vector theta dot of all of our joint velocities. Joint velocities, right? So for example, we could write out this theta dot in full as, right, the rate at which our first joint is spinning, the rate at which our second joint is spinning, and so on and so forth, all the way until the last joint, right? So we want to find a map from this vector into the rigid body velocity, the end of our arm, okay? So we're going to get a map from this into the rigid body velocity of the end effector of our robots, okay? So just remember that the end effector is just that point, like all the way at the end of our robot arm, right? That's what's actually going to be interacting with our environment, okay? So what's the setup for this problem going to look like, right? Well, let's just go ahead and set up a super simple looking robot. We'll just use it as like a test example here, just so we could have something to visualize. But we're going to formulate everything abstract, all right? So I'm just going to write it in terms of this simple robot. All right. Let's talk about simple robot. So let's just say that we have 3 different revolute joints out here, right? Just going to keep it nice and easy. So we have our first joint, right? We have an angle of revolution theta 1. Then we have our second robot joint. We have a second angle, theta 2, that we can spin around. And then we have some third robot joint all the way out here with a theta 3, okay? So the first thing I'm going to do is I'm going to establish a spatial frame or a base frame. So base slash spatial frame, okay? And I call this frame S. So we have like an XS, a YS, and a ZS, right? And then second, what I'm going to do is I'm going to use our terminology all the way from way back when, before kinematics. I'm going to say I have this tool frame over here, right? So this is the tool frame. We call that T, okay? So we're going to have XT, YT, and ZT up there. All right. So what we want to do now is we want to try and find the following. Let's start out by finding our spatial rigid body velocity between our spatial frame and our tool frame. Okay, so I'm going to denote this VSTS, just like that. Right? So this is our rigid body velocity. Between our spatial and tool frames. Okay, let me rewrite that. Tool frames. All right, so this is our general setup, right? And not only do we want to find this just as some arbitrary function, but we want to be able to find a map from our theta dots that's going to give us this value. Right? So if our theta dot, remember, is that vector for our actual velocities of each of these joints, right? Theta 1 dot, how quickly this axis is changing. Our theta 2 dot, how quickly this axis is changing. And then our theta 3 dot. Remember, we want to go from here into our VSTS all in one go, right? How are we going to achieve this? Right. So how do we get this transformation? Okay. So do we have any questions about our setup in this problem before we actually get started on figuring that out? Yeah. Yeah, exactly. Yeah. So we're going to talk about like an actual formal definition for it in just a sec. But yeah, that's what it's going to be. All right. Yeah. Oh, okay. Thanks. Oh, okay. No worries. All right, cool. So how are we going to think about this different, this transformation right over here? Well, something that we can think about is something all the way back from our forward kinematics days when we were still young and before midterm one. What are we going to do? Well, what we know is that each of these axes has a twist associated with it, right? So every axis has a twist, right? So we have like a xi1 for our first axis, we have a xi2 for our second axis, and we have a xi3 for our third axis, okay? So what do each of these twists look like? Well, we remembered that if we take like the ith twist, by accident, I call it xi I, right? This I just means it's either 1, 2, or 3. What we're going to end up with is some component up here. We're going to have this pi, and we're going to have this omega I down here, all right? Now, what we remember is that for revolute joints, omega I has unit magnitude for these twists, okay? So what does this have anything to do with finding our actual rigid body velocities? Well, if you guys did the previous homework, then you might have showed or stumbled upon this fact in there that these things are actually just exactly rigid body velocities, right? These twists are rigid body velocities. Are rigid body velocities, right? Like if we go all the way up and we look at our form for rigid body velocities, right? We'll find that each of these spatial will have that same exact thing, right? It's gonna have that Vs and then that omega s, right? Just with these V spatials, we're not necessarily limited to having a unit magnitude for our omega, okay? So our only difference is with these i's, right? We now have this omega with a unit magnitude, right? So how do we fix that? How do we go from this twist xi to an actual component of our total rigid body velocity? Well, we know that we have the rate at which we're going around each of these axes, right? So let's try to combine it, right? So let's multiply our rate, theta dot I, right? Our speed about this axis, and the twist, and the twist. Okay, so if we do xi I times theta dot I, what are we going to get? Well, let's just multiply that component by component. Vi times theta dot I, and we have an omega I times theta. Okay, so now what we have is we're spinning about this axis omega I, right? But we actually have this velocity associated with it, right? We have this correct angular speed theta dot I. Okay, so now we spin about the axis. Our axis omega I with velocity, or angular velocity, excuse me. Angular velocity theta I dot. Okay. So what this is doing is it's giving us the correct magnitude of our rigid body velocity associated with this joint. All right. Okay. So what this is the rigid body velocity associated with moving joint I at rate theta I dot. Okay. So if I go back up to my picture from earlier and I say, okay, I'm going to spin theta 1 with theta 1 dot, all I need to do is I need to take my twist xi1, just multiply it by that rate. That's going to give me the rigid body velocity associated with moving joint 1. All right. Same thing for joint 2. I take theta 2 dot, I multiply it by xi2. We get the rigid body velocity associated with moving the xi2. Okay. So do we have any questions about this setup right here before we move on and start combining these? What do you think? Yeah. Yeah. So what VI was it was that component of velocity that results from, or it was that. So it was giving us for like every rotation that we have, it was giving us the amount that we translate. So if I start over here and then I move over here, that VI is going to tell me the amount of translation that occurred. So when we're scaling it up by this theta dot I, we're saying that the amount of translation that happens is going to be affected by the speed at which we rotate. So we're just scaling up like that translational amount by the rotational speed. Yeah. Sure, yeah. All right, do we have any other questions? Are you guys for them? Okay. So then our main question, right, was how do we find our VST spatial, right? We want to find the velocity of our tool frame with respect to the spatial frame. Okay. Well, maybe something that we could do is now, right here, we know how we're going to describe the velocity of each of these individual robot lengths, right? So why don't we just try adding them together and we'll see if we figure out anything nice, figure out anything convenient. Okay. So our main idea is we just add together components of rigid body velocity. Velocity from the motion of each arm. Okay, because if we just sum up the amount of velocities from each arm that we're getting, right, we're going to end up with the total rigid body velocity for end effector. Right? The end effector is all the way at the end, so it's being affected by all of these intermediate velocities along the way. Okay, so how are we going to write that? Well, in our case, we only have three of these, right? So we're going to say VSDS is equal to xi1 times theta1 dot plus xi2 times theta2 dot plus xi3 times theta3 dot. Okay. And in the configuration of the robot that we gave you guys all the way at the top, right, where it's just pointing out straight, all its angles are at 0. This is something that's entirely true. Okay. So this gives us a correct formula for VSTS when theta1 plus theta2 plus theta3 equals 0. Okay. So when all of our joint angles are at 0, this is going to be perfectly fine. All right. Now, why is that? Well, when we were doing our forward kinematics, right, we always found our twists in the reference configuration of the robot. It was this configuration where it just looked like how it was in the picture, right? We hadn't actually moved any joints yet. We were just like, all right, freeze all these angles at 0, find the twists, we're good. Okay. So that's what we've written down at the moment. We've written down our velocities for reference configuration. But we don't necessarily want just that reference configuration velocity, right? We want it for any arbitrary position of our robot. So how are we going to deal with that? What will that look like? So what we want was this for any theta, right? For any vector theta, equals theta1, theta2, theta3, right? So what might that look like in this case? Well, I just redraw our robot over here. You know, maybe our first joint will be coming down this way. Then our second joint will be going back up that way. Right? So we have our theta1, our theta2, and our theta3. Okay. So how does this affect our rigid body velocity? Okay, so what are we going to do from here? Well, let's take a look at each of these twists and we'll see how they get affected by this change. Okay, so first off, let's look at this xi1, right? It's this one that's associated all the way with our first transformation. Okay, so what happens to xi1 as we move our robot? All right. So I'll just denote this with this little xi1 prime to denote xi1 at the new configuration. So this is xi1 at a new config. Will xi1 prime be any different to our original xi1, right? If I spin around this first axis, is that moving anything on my first axis at all, right? No, right? So our xi1 is actually staying exactly the same, right? And these further out axes, they're also not being affected by, or they're also not impacting our xi1, because if I have a change all the way out here, it's not going to impact what's happening back at my shoulder, right? That stuff is just limited out there, okay? So because this xi1 is just already on this first axis, right? It's not being moved around by any of these other joints. So as we move to an arbitrary configuration, xi1 will just stay the same, okay? So it doesn't change. Great. It's pretty nice. What about xi2? So what about xi2? How do we figure out what this xi2 prime is? Well, here's our problem, right? In this case, we've already rotated around by this angle theta1, right? So when we try to find the xi2, we know that we already have this rotation that's occurred that's affected the entire position of this twist xi2, right? Okay. So how are we going to deal with that? What are we going to do to take care of this problem? So we know that in our reference configuration, it was pretty easy to find xi2, right? We just use those techniques from forward kinematics. It's pretty straightforward, right? We find our axis, we find a point on the axis, blah, blah, blah. Okay. But what are we going to do in this case here? Well, something that we know is that if we move along with our arm as it's going in space, right? if we move along with the motion, so move with motion of theta 1, right? We look at what's happening to our twist as we do that. If we move along with our theta 1, xi2 is going to look the same, right? Because if I'm swinging this thing around and I'm moving with that point as I'm going, my twist will look exactly the same, okay? So if we move with theta 1, xi2 appears constant. Okay, so all that this means is that our transformation from our xi2 to our xi2 prime, right? The actual xi2 in the spatial frame. The only thing between those is a simple rigid body transformation about our first axis, okay? And because of that, we can write it as the following. It's going to be the adjoint of the rotation about our first axis, right? The adjoint of this G1 multiplied by our xi2 in the reference configuration, okay? So all that we're saying is take our reference xi2, and then we want to transform it back into our spatial frame, okay? So transform into spatial frame. All right, so remember, earlier we defined these adjoints, things that take us from things that are moving with our rigid body transformation, right? Moving with the transformation G back into our actual spatial frame. That's all that we're doing here, right? We know what this xi2 will be as we move out this robot joint. Now all that we need to do is transform it back into our actual spatial frame, okay? So this is what gives us our xi2 prime. So do we have any questions about why this adjoint popped up here, like what we're doing, or why this was something that we need to do? Yeah.
What's that thing? Transform something into frame or into that?
Oh, yeah, transform into spatial frame. Sure. Right. Yes.
So what's the frame of this?
Yeah, so initially everything is going to just be like in the spatial frame, right? Because we haven't actually moved any arms yet. But if we track like our xi2 as we're moving our first arm, it's going to look the same from that moving frame. But what we want to do now is transform it from that transformed moving frame back into our spatial frame. Okay, cool. Yeah, because overall we're just trying to find the spatial rigid body velocities. We got to make sure everything's with respect to the correct frame. Yes.
So trying to put it in the body frame.
Yeah. Yeah, so what you can imagine is that you're fixing a frame like right over here, right on the second axis, and we're sort of spinning it around with that arm. Yeah. Yeah, good question. Any other questions? How are we doing? Cool. Okay. So then what we've done here is we've now figured out our twist. Figured out our twist for any value of theta 1, right? It's not going to get affected by those further out joints. We know that it's just going to be theta 1 that's impacting this twist, right? It's the only joint that came before it. It's the only thing that's going to move. Okay. So now let's move on to our last twist, right? What about xi3? Okay. This one's going to be the most complicated. Oh, sorry, did you write this one? Oh, so G1 is going to be like e to the xi1 half theta 1. So G1 is just referring to the rotation about our first axis. Yeah. All right. Yeah. So just I'll write shorthand. I'll call this G1 as e to the xi1 half theta. Okay. Yeah. Thanks. All right. So what about xi3? How are we going to deal with that? Okay. Well, it's going to be pretty much the same thing as before, except now we have two joints moving before it. Two joints moving before it. Okay. So if we want to figure out where xi3 goes as we're moving this arm, right? First, we need to look at the motion theta 1 around the xi1. Then we need to look at the motion of this theta 2 over here, right? So if we check out the motion, the transforms associated with both of those joints, right, we'll be able to figure out what happens to our xi3 as we're moving this robot arm around. Okay. So let's multiply not only by the adjoint of our first transformation, but by the adjoints of our first and second transformations. Okay. So it's going to be the adjoint this time of the transformation in our first joint, which I'll just call G1 for short, multiplied by the transformation of our second joint, called G2 for short. Okay? And just note that G2 in this case is equal to e to the xi2 hat times theta 2. Okay. So overall, let's just write out what that looks like. So we're going to have the xi3 prime, which is our xi3 transformed to the spatial frame after we've moved our joints around, right? It's going to be the xi3 prime is equal to the adjoint of G1 times G2 times our original xi3 reference configuration. Okay. So does that make sense how we got to this xi3 prime here? Yeah.
Just a general question.
Mhm.
Adjoint of G1,
Yeah, that's a good point. So adjoint of G1, G2 is the same thing as taking the adjoint of each of those individual ones. G1 times the adjoint of G2. Yeah, great point. All right. Do we have any other questions about this? Okay, cool. So let's actually go ahead and apply this formula, right? Let's apply this formula. So if we want to find the overall velocity, oh yeah, go ahead. Yeah, that's right. So when we move like around theta 1, around theta 2, that's moving our axis in space for theta 3. So that's going to affect what that twist will look like. Yeah. But since it's actually like on its own axis, this third rotation, this theta 3, won't end up affecting it. Yeah, because it's just spinning around itself pretty much. Yeah. Yeah.
So like, you know, the adjoint of the G is G something hat.
Yeah.
G inverse, right?
Right.
So what does the G inverse do here? Because
Yeah, that's a good question. So we have like in general, like v hat body equals what should I call it? Yeah, so it was so v hat spatial. So G v hat body, G inverse, like this one, right? Yeah. So what this is actually from is called like a similarity transform. So our general idea here is that we want to feed in to VS, right? A point in homogeneous coordinates, right, in frame A. And what that's going to give us back is its derivative in homogeneous coordinates, right? So if we multiply both sides of this by that, we'll have G hat VB, G inverse times QA bar. Okay. But we can't apply this QA to this VB directly, because VB will only take in points in the body frame. So first, we just have to convert this QA into the body frame, and that's what GP or G inverse does, right? So V hat B, G inverse times QA, will just give us a point QB in homogeneous coordinates. Okay? And then if we multiply those two, then we'll have a G times a QB dot, which is the spatial velocity of this point as seen from frame B. And then we just transform that back into frame A, which gives us a QA bar dot. Yeah, does that make sense? So
you have the adjoint of one matrix, right?
Yeah.
This is already in the spatial frame. Like xi2 in our reference frame, it's already in the spatial frame, right?
So it's in our reference configuration. So it's actually like our idea with this plain xi2 without this thing, this prime attached to it, is that our xi2 in our reference configuration looks the same as our xi2 as we're moving with our robot. So it's actually like in the body frame of that arm in particular. So what I'm saying is that, okay, I'm going to look at this point in this reference configuration. I haven't moved yet. And now if I start moving this and I move myself around with that twist will look the same. So what we're doing is we're going from that configuration where we've now moved to this point, and we're like, okay, we know what it is right there, right? It's going to look the same from within that frame as a reference config. Then we're just going to pull it back to how it looks out here in the spatial frame. Yeah, so we're like moving along with it, and then we're like, okay, we're now in this body frame as we're going around. We got to transform that into the spatial frame, which is where the adjoint of that rotation comes in. Okay. Does that make sense? Or
The adjoint transforms from where you like between two frames backwards. Is that what it does?
yeah, sort of. So if I have like a single arm right here that I'm moving around, right? And let's say that I have this I'll call it, yeah, I'll just call it like xi over here, right? And when theta equals 0, it just looks like this side, right?
Right.
Let's imagine that I just fixed like some little coordinate frame on this arm over here, okay? And now what I'm going to do is I'm going to move this arm around, like rotate it into the page like that, right? So my coordinate frame is going to be moving as well, okay? So that's going to be the new position of my coordinate frame. And our twist will be over here. So within that coordinate frame, that twist still looks the same. So now we have to apply this transformation to get it back into the spatial frame. So then, like if this transformation G was associated with that rotation, what we're going to do is to figure out our xi in the spatial frame, which I call xi prime. We just take the adjoint of that new transformation, that rotation about that axis, and then just multiply it by how it looks over here. Yeah. Yeah, sure. Yeah. Oh, yeah. So this is just like a term from linear algebra. So if you multiply it by a matrix G, and then you multiply it by its inverse on the other side, that's called like a similarity transfer. Yeah, sure. All right. Yeah, great questions. Do we have any other clarifications? All right, cool. Okay. So now what we want to do is we want to add up the velocities from each joint. Okay. And these velocities should all be in the actual spatial frame. Okay. So all those in the spatial frame. Okay. So when we add all these together, right, all these contributions from each joint, we're going to get our total velocity between the spatial frame and the tool frame. Okay. So we're going to end up with Vs st will be equal to our first twist, right, xi1 prime, which we know is just the same thing as a normal xi1, right? So it's just about that first axis multiplied by the rate at which we spin around that first axis, right? So this was our first rigid body velocity. Then we're going to add on our xi2 prime, right, times the rate we were spinning around our second axis times theta 2 dot. Okay. So this is compensating now for the new position of this twist, for this new position of the second axis. Okay. And then we're going to add on our third one. Now we have xi3 prime times a theta 3 dot. Okay. So we've gone ahead, we've added together all these different velocities in the spatial frame for an arbitrary configuration of our robot. Okay. So this is true, it is now true for any theta 1, theta 2, theta 3. Okay, so we just use that adjoint to help us figure out a relationship that will hold for any set of joint angles out there. All right. So let's remember earlier what our goal was in this entire process, right? Our goal was that we didn't only want like a formula, right? A function that we plug in some angles into, but we wanted a map, okay? So we wanted a map from our vector of joint angles, right? From theta dot equals like theta 1 dot, theta 2 dot, theta 3 dot, to our rigid body velocity. Rigid body velocity of the end effector. Okay, so we're almost there, right? We have our rigid body velocity of our end effector. We have all of our joint angles in there. We just want to write this thing as like a matrix vector transformation. We're going to be all good to go. Okay. So how are we going to write that out? Well, we have a VSDS equals some matrix times our vector of joint angles, right? Theta 1 dot, theta 2 dot, and theta 3 dot over there. Okay. So remember, when we perform this multiplication, it's like each of these theta dots is scaling a column of the matrix. Okay. So if we look at this formula that we had up here, right? We have a theta 1 dot times a xi1. All right. So theta 1 dot times a xi1. It's the only appearance of theta 1 dot. So I could just make that column xi1. Right? And we have a theta 2 dot times a xi2 prime. So I can make that the second column, xi2 prime. Then a theta 3 dot times a xi3 prime. Right? So these are now the columns of my matrix. And this matrix was exactly what we wanted, right? It was something that takes us from a vector of our joint angle velocities into our actual rigid body velocity. Okay. So we call this matrix JST spatial. And since it depends on the angle that we're at, it's going to be a function of theta, right? Where theta was that vector, like theta 1, theta 2, theta 3. Okay. So it's this map that depends on the angles that takes us from our joint velocities into our actual rigid body velocity. Okay. So overall, we'll write VSDF equals JSDF, which depends on theta, multiplied by our vector joint velocities, theta dot. Okay. And this matrix, JSDS, which you might have guessed by now, is called the manipulator Jacobian. All right. And this S indicates that it is the spatial manipulator Jacobian. All right. So S is for spatial. All right. And the only way, or the only reason that we have that spatial in there is that this is something that's always returning our spatial rigid body velocity. Okay. So returns our spatial rigid body velocity. All right. So that's what the Jacobian is. Do we have any questions about how we've gotten to this point over here? How are we feeling? Good. Yeah. Oh, yeah. So it's just like if we're trying to figure out the velocity due to a bunch of different individual motions, right? Say like I'm moving this way, but then I'm also moving like backwards this way. What I could do is I could just add up my velocities from each of those different parts to figure out my total velocity in space, right? So here, what we have is we have the velocity due to each like individual motion of the arm, right? So all that we're saying is we could just add up the velocities due to our individual arm motions to figure out our total velocity. Yeah, did you?
So the spatial manipulation dependent on data.
Yes.
Because of the different data we send out.
Yeah, exactly. So if you want to think about a way to like reason about that physically, is that like if I have my pen over here and I'm moving in this direction, my velocity is pointing out this way, right? But if it's now over here, I'm moving it, my velocity is pointing over there. So what's going to be returned by this VSDS will depend on the actual position I'm at in space. Yeah.
Quick follow up on that. So we can think of size and actually like use it velocity.
Yeah, so if we look at like the columns of our manipulator Jacobian columns, right? Where we have like Xi1, Xi2, and Xi3, right? What our columns are really telling us is that they are like little components of velocity, right? So they're telling us where our velocity can go, right? All that we're doing when we're getting our actual velocity is we're just scaling these columns and we're adding them together, okay? So they tell us where in space? In space, our robots can move, all right? Because all of our motions of our robot, all of our velocities are characterized by just multiplying these by some simple scalars, right? So if that's the case, then these things are entirely determining where our robot is capable of moving in space. So, right, so our actual velocity is just determined by scaling and adding these columns. Okay, yeah, great questions. Do we have any other questions about the Jacobian or like how we got to this point? Right? Yeah. Oh, scroll.
Yeah.
Oh, other one.
Yes. Thank you.
Sure. See, a lot of people still copying stuff down, so I'll give you guys a sec. Also, if anyone is still working on the homework, don't worry about it. Only around half the class has submitted it so far. So yeah, so you're okay if you're still going.
File like this day, that one.
Oh, I don't know actually. Like usually most people will get it in like one day after the deadline. I think like probably like 80–85% of people have submitted the deadline for most homeworks, but this one I feel like is a little bit trickier. So yeah.
There's only two cars that are tricky, I guess.
So yeah, so it's more of a scheduling thing than anything, because we have homework party and then office hours, and once the semester starts, it's really hard to get room bookings.
No,
Like
no,
literally
one
everyone
we did.
it's like crazy.
The one I couldn't have
So
to-
yeah.
that one was terrible.
Yeah.
Yeah, that was bullshit.
Yeah.
This one's easy, bro.
I think it's harder to get permissions to do like room allocation. Like you have to talk to like some, I don't know, department chair or something. But if you're actually EEC stuff, then it's super easy. You just do like a Google Calendar booking for the rooms, and then you get it. Yeah. But it's kind of funny, like for the room upstairs that we do homework party in, we trade off with 189 and getting that room every other week. So we have to go to that classroom sometimes down the side. So yeah, that's the reason that we have to go there, is because 189 takes that one occasion. All right. Any other questions? There's an idea. We only have 2 homeworks left, so I think you guys will be fine. But... I'll pass it forwards. All right, cool. Okay, sweet. So we want to just do an example, and then we'll continue. Oh, singularities, right? Okay, so we can do, or actually, let's talk about the body Jacobian first. All right, so the body Jacobian. All right. So far, what we've seen of the spatial Jacobian, right, is that we get our spatial velocity, right, VSTS, from doing our JSTS, which depends on our angle theta, multiplied by our vector of our jet velocities, right, theta dot. Okay. So JSTS, it gives us our spatial rigid body velocity. Rigid body velocity. So remember, that's one of those transformations that helps us find the physical velocities of points on our road. So if we actually want to use this VSTS, how will we do that? We'll say that we have some point QA in the spatial frame, right, that we want to find its velocity. We'll say that its velocity in homogeneous coordinates, QA dot, the time derivative of that point, will be equal to VSTS hat times the point in homogeneous coordinates. All right. So this is something that I think comes up in 1D on the homework. So just make sure that once you get your rigid body velocity, you don't just pick out the components like VS from that. You actually have to apply it to your point. Okay. You have to take its hat map, multiply it by your point in homogeneous coordinates, and only then will you have the velocity of your point. Okay. Yeah. So I want to find the velocity. In that case, I'll just be finding the twists for a non-zero configuration. Yeah, but I can do that after if you want. Okay, sure. Nice. All right, let's do that after. Great. Yeah. To be continued. Okay, cool. Oh, do you need the charger?
Yes, you see.
Yeah, I think I do. Okay. All right, sweet. So this is something that's returning our spatial velocity vector. Oh, yeah, sorry.
So
Yeah.
Jacobian transforms our angular velocities to spatial rigid body velocity.
Right.
And we use our spatial rigid body velocity on the points to get each individual points.
Yeah, exactly. So if I have like a single rigid body link, that VSTS is something that describes the velocity of every single point on there, right? But since every single point will have an actually like different velocity, we need to multiply it by that point to figure out what that is. Yeah. So just remember this VSTS, just a transformation. A transformation.
If you do it both ways.
Yeah, you'll get the same thing.
Yeah, I'm just wondering, is it like a general thing, I guess?
Yeah, so that one.
It's not, okay.
That was just yeah. Yeah.
Well, I mean, you can work out if it's.
I'm not sure actually what the rubric is for that one. Just to be safe, I would maybe avoid it. But yeah. All right. So we're getting our VSTS from this, right? Now, what if we wanted to get our body, rigid body velocity, right? So how do we get? We get VST body, right? So remember, this VST body is something that we give a point in the body frame, and it returns the spatial velocity of that point as seen from the body frame. Okay. So how are we going to figure out what that vector is going to be in this case? Well, you know, if we have this spatial Jacobian, maybe there's some body Jacobian out there, right? So maybe we can find a body Jacobian. All right, so what might that be? What does that look like? Well, first of all, we could just start with the relationship between VST spatial and VST body, right? So we know that VST spatial is equal to the adjoint of the transformation GST, right, multiplied by VST body, okay? This is just the definition of what the adjoint is, right? It takes us from one frame back into the other frame. Okay. So what we want is VST body in terms of VST spatial and its Jacobian, all right? So what I'm going to do is I'm going to multiply both sides by the inverse of the adjoint so we can get VST body all on its own, right? Because we know that that's the output that we're going to want from this thing, okay? So let's multiply by the inverse of the adjoint, okay? So just remember that adjoint, it's a normal matrix, right? 6 by 6 matrix. It's something that we can invert. When you just see it, you know, with the special notation with GST down there, you know, don't get swayed by that. Just remember it's an actual 6 by 6 matrix, just like any other. Okay. So let's invert it. Let's put it on this side. Adjoint GST inverse times VST spatial equals VST body. Okay. There's actually this nice fact that the inverse of an adjoint is the same thing as the adjoint, the inverse of the transformation. Okay. So this thing is actually the same as just writing adjoint GST inverse like that. Okay. It's just a little bit cleaner. All right. So let's try and write VST spatial in terms of its Jacobian, right? Because remember, we're trying to find a map from theta dots to our body rigid body velocity. Okay. So this is going to be equal to the adjoint GST inverse, and VST spatial is our JST spatial, right? Our Jacobian, which is a function of theta, multiplied by our vector of joint velocities, right? Which is equal to VST body, okay? Now here's what we have. I'm just going to rewrite this with parentheses. We have this adjoint, GST inverse, JST spatial of theta, multiplied by theta dot, okay? So what we have right here is we have a map from our theta dots, okay? Map from theta dot that will take us, from theta dot, that when we multiply it by theta dot, it's going to give us back our body velocity, okay? So it gives back our body velocity, okay? And because it does this, this was just exactly what we were looking for, right? This must be that body Jacobian that's giving us the map between our joint velocities and our body velocity, okay? So we define our body Jacobian, JSD body, still a function of theta, right? Still depends on our position in space, which is just equal to the adjoint of GST inverse times JST spatial of theta, okay? And just like that, using the single transformation, we can go all the way from this other one that we came up with, right? This spatial Jacobian into our body Jacobian, okay? So this is called the body Jacobian. And just one more time, just to summarize how this thing is used. If we want to figure out what our body velocity is for something, right? We just take JST body, function of theta, and we multiply it by our joint angles, okay? It's as simple as that. All right, cool. So do we have any questions about this body Jacobian or how we got to this one? Yeah, sure. Tell me when. Is it good?
Yeah.
Okay, sure.
This is a quick summary.
Mhm.
How do you write the estimate inverse?
Oh, yeah, so yeah, GST inverse, I think will be like R transpose 0, 1, and I think it is, so I think it's like R transpose P or something like that. Yeah, yeah. So if we write like the adjoint,
Negative.
oh, negative R transpose. Thank you. So if we try to write the adjoint of GST inverse, then it's just going to be like the RP R01. So we're just going to fill that in with this. Yeah, R transpose and then blah, 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 0 transpose. And this one, yeah, negative R transpose P hatted times R transpose. In that case. Yeah. Sure. Okay. Do we have any other questions about the body Jacobian or about anything that we've talked about?
No.
No. Okay.
No, no.
You gotta transform frames.
That's what-
Yeah. I'll just give you guys a second just to write this stuff down if you want. We had a question in the Zoom chat as well. Is it JST or VST? So VST is what gives you the spatial rigid body velocity. JST is a map from your angles to your rigid body velocity. Yeah, good point. Yeah. Sure. Yeah. All right, cool. Okay, so we can move on to do an example. And in this case, I'm just going to go ahead and find the spatial Jacobian just so we have time to talk about the stuff with singularities. Okay, so let's find the spatial Jacobian. JSTS of theta for the given configuration. The given configuration. All right. So in this case, we're not asking you to find it for a general theta. We're just going to give you a specific set of theta values and then just evaluate it like that. Okay. So we're going to have one joint that looks like that. Second joint that looks like that. And our third joint is not going to be straight on, but it's going to be pointing backwards like that. All right. So kind of like that. All right. So that's our theta 1. That's our theta 2. That's our theta 3. Okay. Then we're going to give you a tool frame that looks like this. So tool frame, an XT, a YT, and a ZT. And oh, sorry, that's a spatial frame. Where's this window coming from? Oh my gosh. Okay, there we go. Nailed it. All right, so this is our spatial frame S, excuse me. So that's an X spatial, Y spatial, and a Z spatial. And then our other frame will be over here. So we're going to have something that looks like this. So this is going to be our X tool. This is going to be our Y tool. That's going to be our Z tool. So it's like this is pointing backwards, like off into the page. Okay. Is this drawing clear, or is there anything that I need to clarify about directions or what's pointing where? Okay, cool. Just to make this easier, actually, I'm going to redraw my spatial frame at the same height as the tool frame. Won't have a huge impact on our problem, but just to make it work out a little nicer. Okay, so it's your XS, YS, and a ZS. All right, perfect. So this arm is going to have a length L, and that arm will have a length L as well. Okay, so what's our first step here? Maybe we'll just start out by just filling out a template for what our Jacobian will look like, and we'll just go one by one, find our twists. Okay. So in this case, we have 3 axes, right? Which means that we'll have 3 columns in our Jacobian. So JSTS will be equal to Xi1. It'll be Xi2 prime, right? And then a Xi3 prime. Okay. So we'll see if these Xi2 primes and Xi3 primes are actually affected by anything that's going on here. But we'll get to that in just a sec, right? And this particular configuration that we've given you is theta equals following. So our first angle is at 0, our second angle is at pi over 2, and our third angle is at 0. Okay. All right. And then we have what else do we have? Yeah, I think that should be fine. Okay. So just to clarify, this point right here, where is this located? So our origin is going to be at, minus L in the X direction, because we're going like backwards with respect to that axis. It's going to be at L along the Y direction, and since they're at the same height, it's going to be at 0 in the Z direction. That's the origin of the tool frame, origin T with respect to. Okay. So where do we get started with this problem? Well, first up, we just got to start by finding these twists. Right? Once we find these twists, we'll really be on our way to finishing this thing. Okay, so let's find our twists. Find our twists. All right. So we're going to start out with Xi1. Right? And this is a revolute joint. So Xi1 will be a twist of the form negative omega 1 plus Q1. Remember where Q1 is a point on our Xi1 axis. And it's going to be omega 1. Okay, so what will our omega 1 be for this case? Well, omega 1 is just going to be whatever axis we're rotating around. Okay, so if we check out our twist over here, it's going to be this Xi1. We're just pointing directly along the z-axis in space, right? So omega 1 will just be z, 0, 0, 1. Now, what about negative omega 1 cross Q1? Well, this axis is something that just passes directly through the origin. Okay, so for that reason, we could just pick Q1 equal to 0. And that's going to allow us to write negative omega 1 cross Q1 will just be something crossed with the 0 vector. Okay, 0, 0, 0. Nice. So what does that tell us? This Xi1 is equal to 0, 0, 0, 0, 0, 1. All right, so that's going to be our first twist. Now remember, is this something that we actually have to transform? Right? Do we need to multiply this by any adjoint? Well, since it's not actually being affected by any of these robot arm motions, right? Since it's just already on our first axis, we know Xi1 is just going to be straight up Xi1, right? We already have it exactly where we need it. Okay, perfect. So what about Xi2 prime? How are we going to figure that one out? All right, so what about Xi2 prime, right? So now we have the potential for this to get affected by our Xi1, right? But will it actually be in this case? Well, let's just find it in the reference configuration first, right? And we'll go from there, right? So once again, it's going to have the form negative omega 2 cross Q2, since it's a revolute joint, and then an omega 2 underneath. Okay. So how do we figure out what this thing is going to be? Now, there's a couple different methods of doing this. One of them is that method we were using in forward kinematics, where we actually identify a point, we take the cross product, and we go through that whole thing. And then there's this other method called the circle method, which we've been using for rigid body velocities, right? So we could use FK method. FK method. And then we can also use the circle method. Also use circle method. All right. So bear in mind, all these twists are just rigid body velocities, right? They're just rigid body velocities with theta dot set equal to 1. Okay. So twist equals velocity with theta dot equal to 1. All right. So just remember, if you're trying to apply the circle method and you think you might not be able to, for a twist, you absolutely can. All right. There's not going to be a single problem in there. Just remember to set your angular rate equal to 1, because twists are always around unit axes, and you'll be all good to go. All right. So let's give that circle method a try. Yeah. Oh, yeah. So if we have a twist of the form like V omega, right? And for a revolute joint, in this case, omega is going to be non-zero, right? So for a revolute joint, we want the norm of omega to be equal to 1, right? We always think that they're unit axes that we're taking around. So since omega is our angular velocity about that joint, if we take its magnitude to be equal to 1, that means that our theta dot for that joint equals like 1 radian per second. Yeah. So then normally, like if we have a rigid body velocity like Vs equals V omega, we don't actually care about the magnitude of this thing anymore. Like magnitude of omega is just anything as long as it's a real number. Okay. So here we just have our theta dot will be the magnitude of that, right? Could be any real number out there. It could be 10, it could be 100, but it could be 1 as well. So all that we're saying right here is that when we're working with these twists, just keep in mind that if we're trying to use the circle method to calculate our V term up here, we're just going to be thinking about spinning about that axis with a magnitude of 1 radian per second. Yeah.
Would you mind?
Oh yeah. We could do that right now if you want. Yeah. All right. Cool. Yeah. So let's just review the circle method. Circle method. So did you want to go through like the derivation of it, or?
No, how to use it.
Oh, I just have to use it.
I was in the homework and I ended up doing like the FK.
Oh yeah. Yeah, that sounds like it sucks. Yeah.
want to find the body, you don't have to like use the adjoint inverse, right? You could just convert the twist
Yeah.
to the body frame.
Yeah, so the nice thing is when we're applying the adjoint to a Jacobian, it's just like we're applying it to each individual column. So then what that means is that each column is just in the body frame, which is like what you're saying. Yeah, so it's kind of nice, yeah. All right, sure, yeah. So let's talk about this circle method, what it is, all right? So our main idea over here is that finding twists is hard, right? And we don't like doing that. We have to do these cross products, all this other jazz. It ends up being a little bit messy, okay? So is there an easy way? Is there an easy way to find the components of xi equals v and omega, all right? So last time we actually went ahead and like derived where the circle method came from. So just for the sake of time, I'll just tell you guys how it works in this case. If you want to check out the derivation, yeah, just ask afterwards, or you can check out the recording from last week. But our general idea is this. So omega is the axis that we rotate around. So axis we rotate around. And it's going to have a magnitude of our angular rate for that axis, right? It's going to have a magnitude of our theta dot, okay? And what about v? What's v going to be? So in the spatial case, right, if this twist is something in the spatial frame, this v will be the velocity of a point moving through the origin of S as we spin our joint, okay? As we spin our joint, okay? And this is something that'll make a lot more sense in just a sec when we scroll back up to the picture, but I'll give you guys just a sec to write this down first. Okay, so whenever you hear the circle method thing, just remember, it's just a shortcut for finding the components of your twist or velocity, right? There's nothing more to it. All right, cool. So let's see how that works. What does it mean to find the velocity of a point that's traveling through the origin as we spin our joint, okay? So what we're going to do is we're going to check out our axis over here, right? We're spinning around this xi2 in space. We're going to say, as we're spinning this axis, let's pretend that we have this point attached to the axis, right? It's like rigidly attached to this axis. We're spinning it around, and let's try and figure out where this point is going to be going, right? Where it's pointing, how quickly it's moving, right at this instant in space, okay? So you can imagine that, you know, as we spin this axis around, this point is tracing out this entire circle in space, okay? But right at this instant, the velocity right at this point is pointing along the x direction, okay? So we have this idea that its velocity of that point, right when it's at the origin, that's equal to that little v term in the twist, all right? So that's equal to v, right? So in this case, we see that we're a distance L away from our axis of rotation, and we're pointing along the x direction, okay? So let's write that down. So we have a distance L to the axis, right? And velocity is in our x direction. All right, so what do we know about a twist, right? We're not just looking at any rigid body velocity here, we're looking at a twist, okay? So for a twist, we know that the magnitude of this omega is always going to be equal to 1, right? So we always want unit axes for our twists. So how do we figure out the actual magnitude of our velocity in this case, right? So what is the magnitude of v? Well, in general, right, we have this formula like E equals R times omega, right? R is like your distance to your axis of rotation, and omega is like your angular speed, right? So this is something that you'll write in like physics classes a lot. In this case, all that we know is that the magnitude of v is going to be our distance to the axis of rotation, which is L, multiplied by our theta dot. But since we're looking at a twist, theta dot is just equal to 1, okay? It's going to be like L times 1, or just L, okay? So if we want to write out our entire twist, xi2, we're going to use this velocity, right? And get our first 3 components. So we know we have a velocity of magnitude L pointing in our x direction, okay? That's going to give us an L in the x direction, and we don't have any other components, L0, 0, right? Now, what axis are we spinning around in space? Once again, it's just pointing in the z direction, right? So we have L0, 0, 0, 0, 1, okay? That gives us where xi2 is. So do we have any questions about what that circle method promises there?
It's. I thought that it was supposed to be elevated to this R.
Oh, yeah. So yeah, so it should be like an L for a dot,
Oh, yeah.
but for a twist. Like, so where theta dot is the magnitude of that omega term in our twist. But for a twist, the magnitude of omega is just equal to 1 because we have unit axes for twists. So that just gives us the yeah.
How do we know the velocity once again?
Oh, yeah. So that's what we get by sketching out this like little circle over here. So basically what's going to happen is you imagine that you're spinning like directly about like this axis in space, right? Like that. Okay. And we have our point right over here. And as this point is, moving around, it's like tracing out this circle, right?
How did you pick that one?
Yeah, so I mean, we could just go through the derivation real quick, and I think that might highlight it if you want.
We'd rather go to
Um,
we go to similarity, because I feel like this was covered last week.
okay, yeah, we can talk about that after if that works. Yeah, okay, so our xi2 is going to be like this one over here, all right? And if we look at our actual configuration of our robot, right, our xi1 is 0 in this case. So that means that this second arm, right, the second joint is still going to be in our reference configuration. Okay, so for that reason, this axis hasn't actually moved, right? Xi2 is equal to xi2 prime. So xi2 equals xi2 prime. All right. So do we want to do the lost twist? Because that's something that's similar to the homework, and then talk about singularities, or what do you want to do? Okay. I'm not too sure. Maybe 10 minutes. Okay. Yeah, maybe we could talk about singularities just so we have time to go through it, and then we'll talk about it. Right. Yeah, sure. All right. So I think actually we'll need a little bit of time. We need a little bit of time for singularities. That was a couple of things. All right. So to be continued. All right. So let's talk about singularities. Let me just roll on and have things with singularities. Okay, so what I'm going to focus on here is just getting more of a physical intuition for why these singularities happen. You can go through and do the linear dependence proofs on your own. If we have time, we can do a couple of them, but I just want to make sure that we'll have room to squeeze everything in. Okay, so let's go ahead and let's take a look at our Jacobian, right? I'll just look at the spatial Jacobian for now, just because that's easy to interpret, right? Let's take a look at our one from before. We had 3 different axes, okay? So we had our xi1, that's our first column, xi2 prime was our second column, and a xi3 prime was our third column. So let's just remind ourselves of what these axes are doing, okay? So these axes, when added together, and multiplied by some theta dots. Theta dots will give us a rigid body velocity. A rigid body velocity for our end effector. Okay, so what does that mean? If we think about what these columns are doing then, right? They're actually telling us about the directions our end effector can move in, right? Because if our rigid body velocity of our end effector, right, VSDF, is equal to some theta 1 dot times xi1 plus theta 2 dot times xi2 prime plus theta 3 dot times xi3 prime, right? We know that every single direction that this velocity vector will be able to point in is something that depends entirely on the directions that these xi's are pointing in, right? If we don't have a xi pointing in a certain direction, there's no way we're going to be able to have a velocity in that direction, okay? So xi determine velocity direction. Okay, so these columns of this Jacobian, they're not just things that help us find a velocity, right? They're really, really tied to where our robot is able to move and how quickly it's able to go in certain directions, right? So let's see if we can figure out what happens when our Jacobian will lose a rank. Okay, what happens when we get some sort of linear dependence in our columns? All right. So what does it mean? What does it mean using this interpretation for the Jacobian to drop rank? It's something that people say a lot. So drop rank just means that we have a couple of linearly dependent columns in there. Okay. So this means that for our Jacobian up here, a couple of these columns are going to be maybe scalar multiples of each other, or we're going to have some sort of constants that when we add them together, we're able to get 0, right? So it means that there's going to be some alpha that we can multiply our xi1 by, some beta that we can multiply our xi2 by, and some gamma, so that should be a prime, that we can multiply our xi3 prime by, such that we get our 0 vector when all of these are not all equal to 0, right? Not all 0. Okay. So this is just the definition of linear dependence, right? We're able to find some set of scalars that relates all three of these vectors. We know that they're going to be dependent with each other, right? We could scale them up and scale them down such that they're all going to be pointing in the same direction. Okay. So our columns are dependent. Okay. So what does this mean for our interpretation in terms of velocity? So if we have this dependence, then one of our twists is actually redundant, okay? One of our twists, or at least one of our twists is redundant, right? If we can get that direction, get that twist, just from scaling up and scaling down these other columns in there, we may as well not have it, right? It's just going to be pointing in the same direction as the other two, okay? So what does this mean for the directions that we're able to point our robot in? Well, if one of our twists is redundant, right, then we essentially lose an entire degree of freedom in our robot. Okay? So these twists, remember, determine the motion of our robot, right? They determine where our robot can go. Our robot can go. Okay. So if we're saying that one of xi1, xi2 prime, and xi3 prime is just composed of, like, say, the other two, right? Then we may as well just not even have that one in there. So it's like we lose an entire degree of freedom. So it's like we lose a degree of freedom in our robot, right? We may as well just not even have that xi3 prime in there if we're losing this rank, right? Because that's determining all these different directions our robot arm is able to move. Okay. So that's conceptually what this idea of a singularity is. So whenever we lose rank, we say JSTS has a singularity. Okay. And that just comes from this terminology in linear algebra that when a matrix is not invertible, you say that it's singular. Yeah, that's just the only reason that we use this word singularity. Okay. So what does this sort of look like practically, right? How is this actually going to affect us? And what does these singularities sort of look like when they pop up in practical robot programs, right? So before we talk about that, do you guys have any questions about this like conceptual setup for singularities, like why we're actually losing this direction of motion, or like why this sort of thing is happening? What do you guys think? That makes sense?
We're just writing out zeta 3 as an example, right?
Yeah, yeah. So for example, like zeta 3 prime could point along like xi2 prime. So if they're pointing in the same direction, they're linearly dependent, we're losing direction. So instead of being able to travel in 3 independent directions, now we're only able to do 2 because 2 of those are the same. Yeah. Okay. So yeah, I'll just write that here. So instead of 3 independent directions, we have 2. All right.
Just one clarification. So
Yeah.
this is already considering the limitations of our robot, right?
Yeah.
Because like from the beginning, the robot already has singularities. Like,
Right,
it
right,
can
right.
move. Okay.
Yeah. Okay, cool. So let's see a couple of physical examples of this. All right. So physical examples, and maybe we'll get a sense for what it means to have these velocities pointing in the same direction. Okay. So a super simple example that we could come up with is this one. So we have two collinear revolutions. All right. So this is the simplest kind of singularity that we could get. Okay. So let's imagine that we have one axis up here, right, where our xi1 is passing through. Right? We have theta 1 and the xi1. Then beneath it, we have this second axis. And this one has a theta 2 and a xi2. So now if we have like a robot arm attached to this one at the bottom and one attached to this one, right, and we're swinging these around in space, right, theta 1 dot equals theta 2 dot, then both of them get the same velocity, right? Then both arms give the same velocity or motion, right? So if these two axes line up with each other, every motion that we could have of this robot could potentially be in the exact same direction, right? So instead of having two joints that we're moving, right, is just like we can move in one direction. Okay, so we're talking about this idea that we have this potential that these two velocities are going to line up and point in the same direction. Okay, so we have the potential for conflict for loss of degrees of freedom. Okay, so if we're moving this one around, maybe it'll trace out a path like that. If we're moving this one around, it's going to trace out a path like that. Velocity of that would be the exact same as the velocity of that. So we may as well just have one joint, because these are both producing that same motion. Okay. So, you know, it might seem that this example is a little bit contrived. Like, why would you ever put two joints right on top of each other just like that? Seems kind of silly, right? So let's see where this might actually show up in practice, a robotics problem. Okay. So in practice, how might this appear? Let's say that we have three joints that look a little bit like this. So that's our first one, and then that's this one over here. Okay. So we have a joint like that. That's the distance L, that's the distance L. Theta 1, theta 2, and theta 3, right? So what can happen is when we're moving this robot around, right, we might accidentally swing this arm around so that it just sits entirely on top of that arm over there, right? And you can swing it around that middle joint, then boom, those two axes are going to align with each other, okay? So we have this potential for our other axis to just align directly with that. And then we're going to end up with a situation where we have these collinear joints pointing along the same direction, okay? So by moving about xi2, the axes align. Okay, so do we have any questions about this first case and like what's going wrong here or why this is bad at all? Yeah.
So why is I moving on the sides to with the line instead of the side one or the middle axis?
So if we imagine that this is like fixed in space over here, and then we move like this axis around, so we're only moving around like this axis in the middle. So you can imagine that like I have this first axis over here, and then I'm coming and I'm like spinning around like that, and then suddenly those two are aligning with each other. Does that make sense?
Yeah.
Okay. Oh yeah. So it's like we have like say that this is like my middle axis that I'm spinning around. Okay? I've got like one axis over here, one over here. So I could like spin around this middle axis, and then all of a sudden that one could line up with that one.
It doesn't have to be the same as theta 1, theta 3. It can be like
Right.
separate.
So we're changing theta 2 like arbitrarily. It's like if I take my arm and then I just fold it back on itself, then suddenly these axes are lined up.
What if the L's are different? Is that how it's wrong?
Yeah, if the L's are different, then you should be fine.
Also, I see.
Yeah.
There's no singularity.
Yeah, so if the L's are different, then actually we'll encounter a different singularity where we have three planar parallel joints. That's actually a singular configuration as well.
I see.
Yeah, and we'll talk about that one next, actually. Yeah.
I'm sorry, are there two quantities on the vector?
Oh, so you can think of your end effector as being like right over here.
Oh.
Yeah, so we're just like spinning that around. Do we have any other questions about this? Yeah.
So like the singularity thing is when like you rotate the original and like
So it's like when we rotate our second joint, like we're spinning this guy so that it's moving like backwards around, and it ends up at that configuration where it's aligned with our first axis. So we're like taking it around, and then boom, all of a sudden it's sitting right on top of our first axis. And then those are going to be giving you motion in the same direction, right? So then it's like we have these two axes sitting on top of each other.
So
So
the first one would be like a little bit below.
yeah.
You're saying maybe below.
No, so even if you have like something a little bit low, let me try and draw it like this. So we have something like that, right? We're saying that this guy is coming and rotating around, and then this axis will end up like down there. Yeah. So we're spinning around the back like that. And then we'll end up with something that looks like this case over here. Does that make sense? Yeah, so it's just like, so we're taking this one, we're moving it just around this axis in space, okay? So this axis is spinning, it's moving our outer arm, right? So it's like I have my arm out here, I'm rotating around my middle joint, and then the axis is suddenly at the same point as this one. Right, so I have my axis like pointing up like that, so I have another one up here, right? All I'm doing is I'm just folding around, then these axes are on the same point. Does that make sense? Okay. Cool. All right, cool. So we can talk about the second case. So example 2. And that's just when we have 3 parallel coplanar joints. Coplanar joints. Okay. So let's talk about this case. Why is this case singular without doing any sorts of revolutions? So we have our first joint, our second joint, and our third joint, just like that. Okay. So these are all sitting in the same plane. You could just imagine like they're sitting in the plane of my paper, right? Or sitting in the plane of this board. Okay. And we have our first axis, second, and third. These things are all parallel to each other, right? They're all pointing in the same direction. So you have this theta 1, theta 2, and a theta 3. Okay. So why might this configuration give us a singularity, right? What's the problem here? Well, here's something to consider, right? All of the velocities in this case, all of the velocities will lie in a 2D plane. In a 2D plane, right? If we're only able to rotate about the z-axis, my only motion is going to be occurring in this xy plane, right? So if I sketch out what that looks like, right? Our only motion could be something right here, right? There's no way we're ever going to be moving up in the z direction because the z-axis is what we're rotating around, okay? So let's say that I move my theta 1, right? Just by a little bit, tiny incremental amount. That's going to cause this guy to shift over this way, right? It's going to give me a little velocity right over there. But at the same time, if I move my theta 2, right, by a tiny incremental amount, this is also going to be moving in that direction, right? So in this configuration, if we try to move these theta 1s and theta 2s at the same time, all of those possible velocities will be lying along that direction, lying along that direction, right? So they're going to be pointing parallel to each other. They're going to be pointing along the same axis in space. So we're not going to have any other way to get a velocity along any other direction, right? So for example, if I had a frame over here, they would all be pointing along my x-axis, right in this configuration, okay? So then we go down to 1 degree of freedom in velocity, okay? And the reason for that is that all velocities in this configuration will point just directly along our x-axis, okay? So all velocities point along your x-axis. Okay, so do we have any questions about like visualizing this case or what's going on here? Why we got the singularity? Oh, yeah. So it's like if I move this arm, right, it's going to be tracing out a circle that looks like that. And this one, as it moves around, this one will trace out a circle that looks a little bit like that. right at this instant, when all of these are flat against the page, right, when they're coplanar, if we try to move this, like every velocity vector that we have, let me pick a different color here, will be like either along that direction, right, or along this direction. And this one will be either along that direction or this direction, right at this instant when they're coplanar, right? So they're all going to be pointing along the x-axis, which is just the same direction for everything. So that gives us a singularity since all the velocities are only pointing along the same.
So it could point back.
Yeah.
Okay.
Negative or positive.
Right. So our idea is that by scaling these theta dots, we could accidentally end up with a case where they're like exactly the same velocity vector.
This is what we do the norm. Maybe we can check the norm and do like subtract two of the columns and the Jacobian and then
Oh, yeah.
and then you get the scalar multiple.
Exactly. Yeah. So if you want to prove that mathematically, then just remember this is exactly the same thing as checking linear dependence, but this is just sort of what it looks like in space to have these columns be linear dependent. Yeah.
So this is only the case when all of that packages.
Right.
For example, like theta two is like get close like backward. Then you have a
Right. So they have to be co-connected with each other. Yeah. Yeah. So if we had them like bent like that, then we would have velocity in the y direction as well as the x. Yeah. Great point. Okay. So I think we are at time here. So I don't see anyone else out there, but if you guys want, we could continue to go over the previous example, or we could just talk about homework questions if you guys have those. And yeah, I think we'll just like end the official section from here. I'll stop the recording. Yeah.
How do you know when it's more like
Yeah, that's a really good question, actually. So I think if we give you like a simple motion, or if something is like fixed in space, then I think the circle method is probably the easiest, as long as you have velocities, or excuse me, as long as your joints are pointing at easy angles. So if they're all at 90-degree angles, they're all at zeros, then the circle method is super easy to use. But if we give you something like a 30-degree angle or 45 degrees or something else like that, then it can be a little bit tricky to use the circle to figure out the direction that it's pointing. Yeah. Any other questions? Yeah. Sure.
Dynamics for this week.
Yeah, I can show you guys what the homework will approximately look like. Okay. Let me stop the recording then. All right. Thank you guys for coming on Zoom.